We're going to be looking at capacitors in detail, which we know a little bit about. A capacitor is just two, well, the simplest capacitor at least is two parallel metal plates. And when we have a charge, positive charge on one and a negative charge on the other, then we have a uniform electric field inside. And so we can essentially use it as a way to store charge in the system. And so how do we get a charge on a capacitor? Well, here's a simple little circuit. Maybe we can show this with the dot cam. Let's see if this actually shows up. Okay, we've got it. So let me see if I can zoom out a little bit. So here's a circuit, right? I've got batteries, positive and negative terminals with two batteries connected to each other, running to this little black thing here is a capacitor. Okay, it doesn't look like two plates, but what it actually is two metal strips or foils that are kind of wound around each other. And there is, as we've talked about dielectrics, there's a insulating material, a dielectric material that separates the two plates and keeps them apart. And so you have two leads, one to the positive plate, or one to the one plate, one to the other, depending on how you charge it. One's positive, one's negative. And then I'm going to connect this circuit I'm going to connect the capacitor in series with just a light bulb. So here's a light bulb. And so let's see what happens. And I'll just kill the lights for just a second here. So I connect the light bulb, battery, and capacitor in series, and the light bulb lights up. And it seems to keep getting dimmer. And it's getting dimmer, and dimmer, and dimmer, and dimmer, until finally it goes out. So presumably the current goes to zero when the light bulb goes out. So what do we just do? We just charge up the capacitor, right? We just charge up the capacitor. Some current was flowing and some through the circuit for some amount of time until the two plates, or the two leads of the capacitor, were charged up. Let me disconnect the capacitor from the battery and have it in series with just the light bulb. So here's the capacitor and the light bulb in series, and I connect the circuit, and the light bulb lights up. And it gets dimmer, and dimmer, and dimmer, until it goes out. Okay, so then the current is presumably zero. So in this case, what do? Yeah, we discharged it, right? We discharged the capacitor, right? So we're going to be looking in detail at sort of the microscopic level, focusing on this level of detail we've been using, namely looking at charges, fields, and how they're affecting electron currents. And think about in detail what's happening in charging and discharging the capacitor, okay? And first thing we have to think about, is this a steady state when we charged it or discharged it? Technically, no, right? Because things are changing, right? If the light bulb has a current in it, and that current eventually goes to zero, then something was changing, right? However, it's not instantaneous. It takes a little while. So in some approximation, the book tends to call it a quasi-steady state. You know, it's not exactly a steady state, but since it takes so long, it took like 30 seconds or something to see this light bulb actually go out, that at any given moment over a short time period, it's kind of like a steady state. So we can still use some of the rules and principles we've been using. Let's just look first of all at we'll look at the discharging case first because that's a little bit easier to deal with. So let me give a question here. So here's a simple model of our circuit when we have the capacitor in series with the light bulb. And let's say it's initially charged up. Okay, we have positive charge on one plate, negative charge on the other. And just from what we saw, just from what we observed, what can you say about the current? What's happening to the current in this circuit versus time while we're discharging? Okay, just just based on what we just saw. And this is a plot of current versus time. Okay, current versus, this is not clear. Current, either electron current or conventional current, doesn't matter. Whichever you like to think about, is on the y-axis. Time is on the x-axis. So how would current versus time look? You can think of time 0 as when we first connect the circuit together. Okay, pretty obvious, right? I mean, we can just see how the current first snaps on, gradually decreases until it goes to 0. Okay, so there's this, it's kind of suggestive, looks like an exponential decay. Turns out it, for ideal situations, it is. We won't go into that today precisely. Basically what's happening? If you have initially two plates, say the left plate is charged negatively, when you connect the circuit, what happens? Okay, this should be fairly straightforward. Okay, so clearly, right, left plate's getting more negative. The current is going to 0, so that must mean the charge is going to 0. And so if we start off with the left plate being negatively charged, meaning the right plate must be positively charged. So the left plate must be getting more negative, and getting less negative, and the right plate is getting less positive, right? Until we go to 0. So we want to think about the mechanism behind this. What's actually causing the charge to move? So here's where the sheets that you have come in. So you have these sheets, and on the top, you have, and so there's two sides. One shows the charging, one shows the discharging. Let's look at the discharging first. Top row, we're going to look at the three little X's in the wire. Draw the electron current at 3 different times. And the first time is 0.1 second after we first connect the circuit together, then 1 second after the circuit's been connected, and then 100 seconds after the circuit has been connected and the bulb is not glowing anymore. Okay, so that's the top row. You can think of, if for the sake of argument, let's say what we drew here is true, that the left plate is negative, the right plate is positive. Okay, so we're drawing the electron current at those locations. When you get done with that, down at the bottom row, same 3 times, draw the electric field at those little X's and the charge distribution on the plates. Draw what the charge on the plate would look like. And keep in mind the relative magnitudes of these vector quantities, right? You want to show if there is a change in magnitude, you want to make that clear. Okay, so I'll give you a minute or two to try this out. Again, we're not turning these in or anything. This is just to get you thinking about this, but I encourage you to actually do it and not just sit and twiddle your thumbs. Okay. Okay, I'm seeing good stuff. Maybe we can take a look at this. Okay, this side's negative, right? So electrons are going to flow. First of all, do electrons go across the gap? No, they're not going to go across the gap, right? Because we've got either air or some other insulator here. There is an electric field here. Okay, the electric field is pointing that way. But essentially, we've got an insulator. The mobility is essentially 0. There's no way for the charge to move across the gap. So the charge is going to move this way, right? And so electrons are going to flow which direction? That way, right? That way. So we have a concentration of electrons here. V, or little I, or I guess we're plotting little I here, goes that way. And little I goes that way. And little I goes that way. So that electrons are leaving the negatively charged plate. It's becoming less negative. Electrons are flowing onto the positively charged plate. It's becoming less positive until eventually it goes to 0, right? So I would draw, well, let's draw the electric field first before I do that. We're looking at time t equals 0.1 seconds. electric field is pointing opposite direction. At this location, it's pointing towards the negatives, right? Okay, and here is electric field's pointing towards that way, and the field's pointing that way. So already we can think about what's causing the charge to move. Well, you have essentially two charge plates, something like a dipole, right? And so outside of the plates, we have the negative charge distribution closer than the positive charge, so the electric field points towards the negative plate. Just outside the positive plate, we have the electric field due to the positive charge. Positive charges are closer, so that field contribution is going to be bigger. Its net field is pointing away from that positive plate. And then presumably there's some surface charge gradient, which I'm not going to draw, but would have to be a bigger gradient across the light bulb, right? So that we get a field pointing that way. And it's the electric field that's driving the charge, right? So this electric field causes the charge to flow because we know that drift speed is equal to UE, or I is equal to NAUE, right? So charge flows. Charge flows, and sometime later, we have less negative charge on this plate. Right? Less positive charge on this plate. Well, if we have a lower charge, then what's going to happen to the electric field? It's going to decrease. So I draw at, what was the second time? 1 second later. You can think of this. As the field is smaller, the field is smaller, the field is smaller. But if the electric field is smaller, then what's happened to the current? It's slowed down, right? It's smaller as well. So the little I is smaller. And we have a blue marker somewhere. There it is. Little I is smaller. Little I is smaller. Little I is smaller. Okay? Until eventually, what happens? At 100 seconds later, the electric field is 0. The current is 0. The charge on the plates are 0. Okay, so you get the idea. It's the electric field, and by the way, there's a name for the electric field outside of the capacitor, due to the capacitor. That has a special name. Anybody remember it? Someone said it. What was it? Fringe field. Yeah, this is the fringe field, right? This is the fringe field of the capacitor because ignoring the surface charge on the wires, if we're just outside the capacitor, this electric field is just due to the charge distribution on the capacitor itself. Much like a dipole, it's going to make a field pointing towards the negative, away from the positive. That is what we call the fringe field. So it's the fringe field that's really controlling everything, right? It's driving the current in the wires, and it's presumably setting up a surface charge gradient, which causes a current elsewhere. Once that current flows to start to reduce the charge on the plates, that reduces the fringe field, which reduces the current, and so on until we get to 0, right? Until we decay down to no charge on the plates, okay? By the way, I kind of skimmed over this, but how should the magnitude of this electric field vector compare to this one? They should be the same, right? It should be the same because we aren't in a steady state, but if we're in what we call the quasi-steady state, if things are changing very slowly, then the current at any given instant should be the same everywhere, right? It is decreasing overall, but over a short amount of time, the node rule still applies. If the node rule still applies, if the current is the same everywhere, then in the same thickness of wire, the electric field should be the same everywhere, okay? It's going to be different in the filament because that has a different area, cross-sectional area, but it'll be same in the connecting wires, okay? Pretty clear, right? I mean, questions on this? The basic idea is you have a charge capacitor. It creates an electric field, the fringe field in the wires. The fringe field in the wires causes current to flow. Current flows such that it reduces the charge. The charge reduces, and therefore the field reduces, and therefore the current reduces, and you get this decaying current until you go to 0, okay? So it's sort of a feedback mechanism. creating a surface charge density itself. Let's look at questions before we go on. Let's look at the charging the capacitor case, which is a bit more interesting. Let's say we start off with the capacitor initially uncharged. We just connect the circuit together. What happens to the current? Again, we're plotting the current versus time. Think about what happened in the light bulb, because the light bulb is essentially giving us our measurement of the current. The brighter the bulb, the greater the current. And time equals 0, again, you can think of it as just after you've connected the circuit. Okay, this always causes problems, and I think it's a misunderstanding of what this question is asking for. You're charging the capacitor, that's certainly true. So something's increasing, right? The charge on the capacitor should be increasing. But what did we just see with the current? Let's do it again. Let's do the experiment again. I first connect the circuit. So here's the uncharged capacitor, right? And put the light bulb back here. And I first connect the circuit, and the light bulb is bright, which means there's a current flowing. Yes? And what happens to that current? It's getting lower and lower, isn't it? It's actually decreasing. So the graph should be, which one? 4, right? Same as the exact graph as the charging case. So be careful of that. The current is actually getting, when you first connect it, it's high, but then it gets lower and lower and lower, which is kind of interesting. So let's think about what's happening. Again, the question is, how can charge actually flow if there is a gap? This isn't a complete circuit, right? We have a gap of air between the two capacitor plates. So the question is, how are the charges flowing? What are they doing? Okay, so no one's saying electrons are jumping across the gap. That's good, because again, as we said, they can't. Okay, the mobility is essentially 0 across the gap, even though there's an electric field. The electrons pile up on the left plate. Well, first of all, we have to determine that from the direction of the current, right? So here's the negative terminal of the battery. Electrons are flowing that way, right? So if electron current is that way, then this plate is going to be negative, right? So electrons are going to build up on the left side of the capacitor, left plate of the capacitor, okay? All right. Same situation. We have on the opposite side of this sheet, you have 3 states, or 3 different times for the charging case. Draw the electron current, 0.1 seconds, 1 second, and 100 seconds after you've connected the circuit. And down below, draw the electric field at those little X's in the wire, and the charge on the plates. What's happening to those at 0.1 seconds, 1 second, and 100 seconds after you've connected the circuit? Okay, I think we're converging to something, and this is, let's see if we can think about this. So we start off with neutral plates, and we know that the electron current, we said, is flowing in this direction, right? At least initially. And a good question came up, which is, well, should it be the same everywhere? Isn't this plate or this capacitor somehow blocking the flow of electron current? We certainly said that electrons can't flow across the gap. So if electrons here are running into the gap, they're making this plate become what? More negative, right? So negative charges build up. Well, there's no charge flow across here, so where are these electrons coming from? What's happening to this plate? It's going to be becoming more positive, right? Essentially, the plate itself is supplying the electrons to flow throughout the rest of the circuit, right? So we have build up a positive charge there, build up a negative charge here, and that continues. And we saw just from observations that the electron current, what's happening over time to the electron current? It's decreasing, right? So it's going down, so eventually it reaches a point like that, and each of these has a smaller electron current. Okay. And then 100 seconds later, we have electron current being equal to 0. All right. So what's happening to the field? Well, again, just following our nose here, that drift speed is equal to U times E. Electron current is N A U E. The field and the current are directly proportional to each other. So, and the field is pointing in the opposite direction of the electron flow. So if we have, draw these arrows bigger again, there's I. Then the electric field is pointing here, pointing in the, what direction? That direction, right? Opposite direction. And I'm drawing the net electric field. The net electric field due to all charges on the circuit, right? And here it's pointing that way. And here it's pointing that way. And what happens over time to the field? It gets smaller and smaller, right? Well, we're looking at the net electric field. What does this field do to? What causes it? Okay, we have the batteries. The batteries have negative charge on this plate, positive charge on that plate, negative here, positive here. Is that the only contribution to the field? Okay, we're going to have the fringe field, right? The fringe field due to the capacitor. That's also going into the net electric field. And there's going to be surface charge on the wires as well, which contribute to the overall net electric field. So I want to focus on sort of this location as just an example. Let's think about initially what we have and then how the field changes as we go to the final situation. So we initially have a net electric field pointing in that direction. In the very initial state, when you first turn the circuit on, what's the fringe field equal to? Fringe field's equal to 0, right? Because you don't have any charge on the plates yet. So this net electric field is essentially just due to what? Just due to the battery, right? The battery is applying, and some surface charge on the wires, but the battery, if we're close to the battery, is producing an electric field pointing in that direction, okay? What happens here? Oh, so let's just ask a question. That electric field of the battery is just supplied by the battery. The battery maintains a constant charge separation, so the field to the battery shouldn't change. But what happens to the fringe field of the capacitor? The magnitude of the fringe field of the capacitor. Remember that electrons are flowing that way while we have a net electric field pointing the opposite way. We see that, okay, good. Everybody's saying that the fringe field is actually increasing, right? Because the charge is getting bigger. Charge is increasing. That means the fringe field of the capacitor, which is pointing which way? Fringe field is pointing that way, right? That's getting bigger. And as you put more and more charge on here, this is E fringe. Put more and more charge on here, E fringe gets bigger until what? Until they're equal, right? Until the electric field of the battery and the fringe field are equal but in opposite directions. They add up to E net equal to 0. You're back to what? not steady state, but equilibrium, right? You're at a point where you reach static equilibrium, and the current is then 0. So you've charged the capacitor fully, and there's no more current going to flow. So the point is, again, it's the fringe field of the capacitor that's kind of that's the governing mechanism. You have this field due to the battery, but as the fringe field grows, the current, the net field goes down, the current goes down, the charge goes up, and eventually you reach static equilibrium once again. Okay? Yes, question. Okay, I'm ignoring it just so that we can easily talk about it, but I'm making an approximation saying that if I'm very close to the battery here, then the field here is mostly just due to the battery and the surface charges. But it's got to be true everywhere. So because we're in a quasi-steady state, we must have surface charge on the wires. And what would it look like? Well, it would have to be when we first start charging, you have negative charge here and positive charge here, and actually some negative charge over here, so that you can get a surface charge gradient across the light bulb, right? So a current is actually going to flow in a light bulb. Once we reach static equilibrium, well, we must have a situation where we have negative charge here, positive charge on this plate, and then, I don't know, let's see, we'd have to have some, well, eventually the gradient has to go to 0, okay? And eventually you have to have essentially no electric field anywhere else in the circuit, so you have to have surface charge arranged in such a way such that electric field everywhere is equal to 0 inside. So I'm ignoring that because it can get kind of complicated and messy to draw. But if you kind of just focus on right next to the battery, or kind of a simple case of the plates right next to the battery, then you can kind of wrap your head around it a little bit more easily. Okay. Other questions? Yes. So in other words, flip the capacitor? Flip the batteries around. Okay, so either flip the batteries around once it's charged, or flip the capacitor around. Yeah, right, because then you'd have the fringe field flowing in, or pointing in for at least an instant in the direction you want, right, in the same direction as the field of the battery, and then charge would flow again until you charged it up the other way. Basically, it would go through 0 and charge up the other way. Okay. Other questions?